A very good day to all the participants to this online course on thermal power generation, transmission, distribution organized by National Power Training Institute, Durgapur. And today's topic, what we are going to discuss, is on power station layout. Basically, as you know, thermal power plants play a very prominent role in total power generation in the country. In fact, around 70% of the total power generation is still now dependent on thermal power, that too on fossil fueled fire generation process. And in this context, if we see that the process of coal to electricity generation, there is specifically to see that it is a process of energy conservation, energy conversion. And this energy conversion is actually taking place in such a way that we are getting the chemical energy stored in the fossil fuel is converted into thermal energy, and this thermal energy is again utilized with some working fluid to get into useful work, and this useful work then utilized to create some energy, to create some torque, rotary motion that will run a prime mover, and this prime mover will be connected with a alternator, and this alternator will generate electric power. So basically this is a continuous process of form of energy available in the fuel to get it converted into useful electrical power. Now let us see the basic layout of the thermal power station. Particularly, we will be discussing in context of coal-based thermal power station, and to be specific, pulverized coal-based thermal power station, which are having large utility power generating capacities. Now, in coal-fired thermal power generating plant, basically we have some fuel processing unit where coal as primary fuel and oil or gas as secondary or tertiary fuel is used, and this coal, it has to be received, unloaded, stacked, reclaimed and utilized as well as processed for proper burning in a steam generator or boiler. It has to be prepared, it has to be fired in the furnace, and after firing we have to see that there is adequate combustion taking place, and post combustion the whatever heat is released, they are trapped appropriately in various locations of the steam generator, which is nothing but a kind of heat exchanger with heat traps. And when adequate heat trapping is taking place, the working fluid which we are using, that water, is getting converted into steam, and this steam is then carried to a turbine, steam turbine in fact, so that this turbine can be rotated with this heat energy available with the steam, and steam, once it loses its heat energy, condensed back to water in a condenser, and this heat energy what we are using in the steam turbine, that is converted into kinetic energy to produce torque to run the turbo alternator. And this turbo alternator, when it is running, then we are finding that electricity is generated. Let us start with coal first. Coal as a primary fuel we are using, and it has been found that this run-of-mine coal, which are fossilized fuel, they are not only having the carbon, beside that you have lot of impurities, and these impurities as coming with run-of-mine coals, these are nothing but incombustible materials which we get as residue, as ash after combustion. Now, there are several methods of coal transportation. We may find there are overhead trolleys. Sometimes if the pit head is not nearby, you may find coal is transported by seaports and even in rails or roadways. We have several qualities of coals, but particularly in Indian context, if we see, we will find that mostly grade G, C2G, long flame, high ash coal is used for thermal power generating process, which are having medium volatile matter content and average calorific value up to 3500 kilocalorie, and even we have high ash, high moisture coal having CV, gross calorific value, around 2000. Even that quality of coal also we use for thermal power generation. And coal quality itself is a big challenge for thermal power generation because it affects the operating performance as well as efficiency parameters which are related to coal quality as well as capacity restriction imposed by coal quantity to be utilized for maximum continuous rated power generation. Now, after receiving the coal in the coal handling plant by various transport processes, this has to be unloaded. For rail system, we have unloading system like wagon triplers, and there are tripler cars for coal coming with the roadways, and these wagon triplers and whatever coming through the car, they are actually dumped in a conveyor system, and this conveyor system take this coal to the stacking yard. For transportation of rakes, we have loco and we have various shunting arrangement, we have side pullers, we have tracker arrangement with tripping cars as well as crawler mounted trippers. All these actually help in stacking, and this stacking arrangement is done through conveyor system. There are track hoppers, and from the track hoppers this coal is transported through some conveyor system for crushing arrangement, primary crusher house, where it is crushed and there are granulated crushers, and these granulated crushers, they crush the coal into minus 20 millimeter size, and we have the arrangement to separate the coal fines generated during this crushing and fragmentation, and except this coal dust, this crushed coal below 20 mm size is taken further by a conveyor system to the raw coal bunkers. So, in the coal handling plant, we have coal receiving arrangement, we have coal stacking arrangement, and we have coal reclaiming arrangement, and again we have coal transporting arrangement up to raw coal bunker. The raw coal bunkers are placed in the vicinity of the boiler, and whatever coal is stacked in these bunkers, they are specifically stored in such a way at least for 2-3 days coal feeding stack is available within these raw coal bunkers. There are individual raw coal bunkers for each of the pulverizing system. That means each raw coal bunker is feeding to a particular coal mill. Coal mill is an equipment which is actually grinding the coal just like fine talcum powder. We are feeding this coal in the coal mill from the raw coal bunker through a coal feeder. A coal feeder is placed between the raw coal bunker and the coal mill, and the amount of coal to be sent to the boiler, that is determined by this coal feeder. In the mill, we are grinding the coal just like fine talcum powder, and this pulverized coal or ground coal, that is transported by hot air through some coal carrier pipe to the burners, and from the coal burners, this coal with primary air which is required to initiate the combustion, it is thrown into the boiler furnace, and if there is sufficient heat with prevailing oil burning, with that heat coal start burning, and with that combustion huge amount of heat is generated within the furnace. So as a result of this combustion, the generated heat this heat is transferred to the working fluid, which is flowing through the various water walls surrounding the furnace, and this flue gas post combustion product which is generated gradually transferred the heat and gets cooled, and it flows through the boiler furnace part and then subsequently second pass, and from there with the help of some exhaust fan which is called induced draft fan, this flue gas is exhausted to the atmosphere through a chimney. So we find this coal which we are feeding into the mill, it is getting ground, and after complete pulverizing it is being pneumatically conveyed to the furnace where it is getting ignited and burned, and heat is released. That heat is transferred, and gradually the product of combustion, the gaseous as well as solid, that is generated. The gaseous part is flue gas and solid part is ash, and this ash has got two components. One part is called bottom ash, which is coming at the bottom of the furnace, and other part is flying with the product of combustion, that is called fly ash, which is flying with the combustion product flue gas, and it is passing through different passes, and then it is getting arrested in some dust collecting mechanism, and this clean flue gas that is exhausted through a induced draft fan through the chimney to the outside atmosphere. So far we have discussed about the fuel and flue gas, and now we are going to discuss about this combustion and then how this combustion is taking place and what are the components involved in the combustion process. Now, as we know, any fuel, when we try to burn it, that means it is a kind of oxidation reaction and we need oxygen, and this oxygen, in case of boilers, we provide it through air, and as I have already mentioned, we have some air used as primary air which is utilized for conveyance of coal, transportation of coal in the furnace up to the furnace, and we have also some air which is utilized for completion of combustion, that is called secondary air. So the primary part of the air, which is about 30% of the total air, this is used for drying the coal and flying the coal into the furnace, and secondary air is supplied. This is used for completion of combustion so that we can get the complete heat generation as an exothermic reaction of the combustion. Now, the both primary and secondary air that may be supplied into the boiler by a fan which is called forced draft fan, or we can have two separate fans. One fan is called primary air fan, PA fan, which is supplying the primary air, or there is another fan which is called secondary air fan, or the both primary and secondary may be supplied by a single forced draft fan. whatever may be the arrangement, the thing is that we need sufficient air, including the air which will ensure that completion of combustion is there, so that total heat energy can be released through the process of combustion and which can be transferred to the working fluid. Now, this flue gas which is passing through the boiler, in the air flue gas circuit we have some arrangement which is used as air preheating arrangement, and this air preheater preheat the air so that, as we know, coal is hygroscopic in nature, so we need to dry the coal. If we cannot dry the coal, we cannot fly the coal. So drying is ensured, so that during pulverizer we are not getting paste, but we are getting dry dust of pulverized coal. And this hot air gives sufficient ignition temperature in the combustion chamber, that is furnace, so that quickly the fuel can participate in the combustion process. The exhaust flue gas from the furnace, which is passing through the last heat trap air preheater, then it is passed through your dust collecting device, dust separation and collecting device. We have many types of arrangement, mostly mechanical dust collectors in some of the plants we may get, and in all the plants we find electrostatic precipitators, which is an equipment which charge the ash particles, fly ash particles, and get it collected in some collecting plate in the electrostatic precipitator, and that is again transported to ash handling plant and disposed in some ash dikes. So this way, clean flue gas, after arresting all the suspended particulate matters, are connected to a induced draft fan. That fan exhausts this flue gas, clean flue gas, through the chimney to the atmosphere. So in a nutshell, we find in the power plant basic cycle, we supply water in the boiler as working fluid, and that is getting converted into steam inside the boiler, and that steam is supplied to the steam turbine connected to a generator, alternator, and this turbine where the heat is utilized. After that, the steam, exhaust steam, we are cooling down and getting condensed back to the water in a condenser, and this condensed water again flown back to the boiler for further generation of steam. If we put this practical cycle in the Rankine vapor power cycle, applicable for subcritical regime of operation without regenerative feed water heating, then we find that there is a feed pump, boiler feed water feeding pump, and that pump is doing some work on the water to take it to the boiler. So naturally there is a slight increase in temperature of the working fluid, due to the pump work, and subsequently the entire heat addition is taking place inside the boiler at constant pressure. And there are three phases of heat addition. First phase is sensible heat gain, followed by latent heat gain, and finally superheat gain. So as a result we get dry superheated steam which is supplied to the turbine, and the entire heat addition process is taking place at constant pressure. Now let us see the water steam circuit. How water is introduced in the boiler and how it is gradually heated step by step in different heat trap zones. If we see, water is entering inside the boiler through a heat exchanger which is called economizer. It is the first heat trap in the water steam cycle as well as last heat trap in the combustion zone flue gas air circuit. In the economizer, actually we are having sensible heat addition. There is no steaming and we raise the temperature of water around 40 to 50 degrees centigrade. After that, this water is going to a storage drum where water is stored up to a certain level. In this vessel, actually both water and steam is present. As both are present in dual phase, this is in saturated condition at the particular pressure. From the drum, water is going through the downcomer, going down, and it is passing through the water walls which is surrounding the furnace, and heat exchange is taking place across the furnace water walls. As a result, the latent heat of vaporization is added up into the circulating water. As you see, the water flowing through the downcomer, they are actually in the saturated condition of water, and whatever heat we are adding in the furnace water wall, that is giving the latent heat of vaporization. As a result, whatever minute excess energy is available with the water above latent heat of vaporization, there is a phase transformation. So we get water steam mixture which is again entering the drum, and while entering there are separating arrangement, and this separating arrangement separates the water with the steam water mixture within the steam water mixture, and separated steam in saturated condition come into the steam space, and from there is arrangement to dry the steam and clean the steam from moisture, and dry saturated steam comes out of this to go for superheating. So we find there is a continuous circulation due to thermosyphonic action which is generated due to density difference between the water column in the downcomer and water steam mixture column in the furnace water walls, and this density difference gradually decreases with rise in pressure. In that case, we install another pump which is called circulation pump. However, due to this circulation and continuous separation of steam, we continuously introduce water inside the drum and take out saturated dry steam out of the drum, and that is taken for superheating. This superheating is done in 3 phases. The first phase is called primary superheating, and sometimes this primary superheating is done in 2 phases: low temperature superheating at second pass and primary platen superheating at the top of the furnace. From the primary superheating, we send the steam for secondary superheating or final superheating, and in between the primary and secondary superheating, we have the arrangement to control the steam temperature by desuperheating or attemperation. In large utility boilers, we have a separate arrangement for enhancing the total cycle efficiency, which is called resuperheating or reheating. In this arrangement, the superheated steam, which is taken out of boiler and sent to high pressure turbine, after expansion in the turbine, it is taken back to boiler for resuperheating. This resuperheating is done up to the temperature in which superheating was done, and after this resuperheating or reheating at lower pressure, this steam is again returned back to turbine in intermediate pressure stage or medium pressure stage, where it is expanded, and from there it is passed on to LP turbine, low pressure turbine, and finally the exhaust steam is condensed in the condenser with circulating water, where the heat is rejected. So, reheating is another additional arrangement for large utility boiler to enhance the cycle efficiency and to get back more work output from the steam. Let us now review the modified Rankine cycle for subcritical pressure regime of operation. And if you see that in the actual vapor power cycle, modified Rankine cycle adopted for coal-fired thermal power station, the process want to represent the work done by condensate extraction pump. So it is the CEP work, and 2 to 3 it is part of low pressure regenerative feedwater heating with steam extracted from LP turbines and MP turbine. So LP heating is there between 2 to 3, which is adding up heat in the condensate. Then 3 to 4 again, if you see, that is work done by boiler feed pump. there is slight change in temperature of the feed water due to this work, and discharge of the boiler feed pump, that feed water is passed through HP heaters, high pressure heaters. 4 to 5 represent high pressure heating arrangement as a part of regenerative feed water heating, where blade steam is taken from HP turbine and MP turbine. Now, from 5 to 6, it represents the various stage of heating in economizer water wall. And as you see that our drum, steam drum or water steam drum, that is placed outside the heat transfer zone. So water in the drum represented by 0.5 and steam in the drum represented by 0.6, because both are in saturation stage. From 6 to 7 it represents superheating, and this superheating, as I already mentioned, it is taking place in 3 stages. And after superheating there is expansion in the HP turbine. 7 to 8 represent HP turbine expansion in the HP turbine. So post expansion of the steam in the HP turbine, it is again taken for resuperheating or reheating. So 8 to 9 represent resuperheating or reheating in the boiler, though you see the pressure of reheating is less than the pressure of superheating. So naturally degree of superheat is more in case of reheating. After reheating, we have expansion in the intermediate pressure turbine, that is IP turbine, 9 to 10, and 10 to 11 is the expansion in the LP turbine. In fact, if you see this total cycle work output, the maximum work output is coming from the LP turbine, and from 11 to 1, that represent the process of heat rejection in the condenser. And in the condenser we have circulating water continuously flowing through it, where heat is rejected or heat is taken away from the exhaust steam to make it again in the form of water or condensate, and that condensate again pumped back to the boiler successively by CEP and BFP. So this is the cycle. So far we have discussed about the process plant, process layout for coal-fired thermal power generation, and how these processes are integrated within the plant. Now let us focus on power plant layout. And if we see the layout, there are basically 3 kinds of layout pattern. First one is site layout, then station layout, and main plant layout. And layout actually should start with the general detailed project report itself, where we try to focus on the topography and geographical conditions, and we have to see the main major resources and connectivity of power and roadways and load conditions, how generated power can be distributed to the national grid, And we have to see also how speedily the construction can be taken at ease, and how protection has to be introduced in terms of nearby river and level of the locality in terms of sea level or river level. We have to take care of road connectivity, rail connectivity, and as well as how to take the water within the plant and how it has to be processed for the purpose of CW circulating water supply as well as main plant water requirement. In fact, for main station, we have to see also the how transmission routes should be channelized and how CW circulating water system should be routed within the main plant, and how fuel supply arrangement and ash disposal system and liquid waste disposal system can be routed. There should be adequate consideration for infrastructure setup that is required within the construction phase itself for administrative purpose, for main plant purpose, for transmission, distribution and switchyard purpose. All this has to be taken care of. When we talk about station layout and when we talk about plant layout, for plant layout, process fluid flow, how it is taking place and how economically the available space is utilized. Those are the main considerations. Along with that, we have to see the ease of installation, operation and maintenance activities, and there should not be any point of interference among the different groups who are working in operation or maintenance or servicing. There should be clear passages and easy access to various floors and equipment for checking, monitoring and controlling, and above all, safety precautions, how they can be incorporated for the entire plant. And there should be cleanliness and arrangement to check out the total controlling of the plant, main plant and balance of plant and other off-site facilities. For large utility boilers, we have larger turbines, and these steam turbines are actually multi-cylinder. That means they are having high pressure, intermediate pressure and low pressure cylinders, which are also called HP turbine, IP turbine and LP turbine. These turbines, as the name suggests, they are handling steam at different pressure, and HP turbine itself is having the highest pressure operated steam turbine, and from the HP turbine, for bigger units, exhaust of the HP turbine is used for resuperheating or reheating. Before that, steam is, after reheating, is introduced to the intermediate pressure turbine. So in the HP turbine, we have high pressure expansion and we have arrangement to control the steam injection within the turbine by governing, and we have nozzles. Beside that, there are bleeding from the HP turbine. These blade steams are used for regenerative feed water heating system, particularly high pressure heaters where non-contact type heating arrangement is there. In case of IP turbine, mostly it is dual flow type. That means flow is taking place in both the directions from the injection point. And after expansion, this steam is taken to the low pressure turbine. In most of the plant, we will find that these turbines are placed successively and they are coupled together in such a way that they are working in unison as a combined unit of turbo alternator. So HP, IP, LP and alternator all are coupled together, and together they are called turbo generators. As we find that turbo generator itself is placed in certain elevated level. In the elevation where we have control rooms and where we can have some access to the connectivity for different bleeding arrangement as well as to accommodate condenser at the bottom of the LP turbine. Beside that, we have arrangement to demineralized water feeding at hot oil which is attached to the bottom of the condenser. The generator which is used in most of the power plants, thermal power stations, they are three-phase generators rotating at 3000 rpm. That means they are generating power at 50 Hz and the output voltage is 11 kV, and for 210 megawatt unit the generator rating is 247 MVA. The generator is also attached with exciter. Excitation system is there, and along with that AVR and other automatic voltage regulator and other arrangements are also present. So the entire turbo generator is laid horizontally according to the availability of space in such a way that it can accommodate all the components of turbine and generator and excitation system. Let us now see some typical layout arrangements which are provided in different plants according to the convenience. The first one is showing the different orientation of boiler plant and its auxiliaries. If you see this, that towards the chimney in some plants you have the milling system layout, coal bunkers and mills, and in some plants you will find that unit wise this layout is such that milling system is between the boiler and the turbine bay. So this way we have different layout plans according to the convenience and provisions of the plant spaces. In the next one we see a 500 megawatt unit, coal-fired unit elevation layout. In this, if we see that boiler is placed between the turbine floor and the chimney, and if you see the layout, it is a compact arrangement in such a way that all the elevations are utilized properly with requirement of CW intake system and power connection to the switchyard, to the generator transformer, and the boiler plant milling systems are placed in such a way that it is ease with the coal carrying piping arrangement from the coal mills with reference to furnace. So this way plant layout varies location to location, plant premises to premises. In certain locations we find the common facilities are made in such a way the unit by unit are made in parallel. So we find all the milling systems are located between the chimney and the boiler, and conveyor systems are attached to them, so that from a common conveyor feeding can be controlled. There may be different layout depending upon the space problem. The diagonal layout arrangement of the turbo generator shows that the space arrangement is made in such a way that turbo generator is diagonally placed for the better control of the system, process flow, and accessibility of the various locations of the plant. Switchyard is the station level layout planning, and it requires a lot of space, and generally it is always preferred to have the switchyard in such a way it is accessible for all the units for initial power supply as well as generated power evacuation. In general, switchyards are placed in such a way the fire safety arrangements as well as cleanliness can be maintained, and appropriate overviewing of the performance of isolators, breakers, transformers, their maintenance, servicing, that can be taken care of. Let us now review the common facilities which are required as off-site facilities with reference to the main plant. In fact, all the units are utilizing these common facilities like circulating water system or CW system, coal handling plant, oil handling plant, water treatment plant for service water and demineralized water, ash handling plant, switchyards, and centralized buildings for administration, control, maintenance activities, servicing, and recording. Water availability is the major common requirement for offsite facilities, and there is various requirements of water. because we require water for ash slurry disposal. Water is required for cooling purpose, and water is also required for generating steam and also for drinking purpose. So, looking into the various requirements, the processing of water is done in different phases. Initially, the raw water, surface water, which is connected, it is passed through aerator to clean it, and there is clarifier, and where we dose alum and lime and pass through pressurized sand filter to remove all the sediments, and after that, if it is used for drinking purpose, we pass it through chlorination process, and this clarifier, actually clariflocculator it is called, and after chlorination this water is supplied as drinking water, and the water that is cleaned, pretreated, that is further processed for preparing the demineralized water, and there is chain of arrangement for demineralizing the water to make it suitable for use in the boiler. For that, we have activated carbon filter, weak acid cation, strong acid cation, then degasifier, then weak base anion and strong base anion, and mixed bed. And from through this train, when we pass this clarified water, then we get demineralized water with pH level 8.5 to 9, and this is stored in DM storage tank and subsequently used for boiler water purpose. We require a huge quantity of water for circulating water requirement. That water which is absorbing the rejected heat of exhaust steam from the LP turbine, and circulating water requirement, if we see, it is 200 cubic meter per megawatt per hour. A huge quantity of circulating water, CW system water is required. And we have different types of cooling towers. We may find natural draft or forced draft cooling towers, and these cooling towers are placed in such a way there is certain gap is maintained between them, and there is some reservoir for CW system from where CW pump can take up water for circulating purpose and utilize it. In fact, the CW system is made in such a way all the units can utilize them from a single location. Most of the coal-fired power stations, we are using coal as primary fuel, but to initiate combustion of coal, we require proper ignition temperature and support sustainability of the flame. For that, we utilize heavy furnace oil or light diesel oil or diesel depending upon the availability, and oil is used as a secondary fuel for the furnace. In some of the places, natural gas is also used where it is available, or Corex gas or CO gas, depending upon the availability. The oil handling system is one of the offsite facilities which are used for common purpose of all the units available in the station. There is decanting arrangement where oil coming through the rail are unloaded, stored, then pumped, and we have oil heating facilities so that oil can be, high viscous oil can be pumped to the boiler to support flame or to initiate combustion. Regarding ash handling plant, we have already discussed about the formation of bottom ash at the bottom of the furnace and fly ash which is accumulated and arrested in the electrostatic precipitator and mechanical dust collectors. All these ash particles are transported by ash handling system and ultimately dumped in the ash dikes, ash ponds. So we find all the station based layout are arranged in such a way that common facilities are surrounding the main plants and the boilers are placed side by side. There may be a common turbine floor, switchyard may be common, there may be common oil handling, ash handling and coal handling plant. Cooling towers may be placed at a particular location, and we have DM water treatment plant in a common place which is suitable to supply DM water to all the boilers. Thank you and best wishes to you all on my behalf and on behalf of NPTI Durgapur. And if you have any queries, please do not hesitate to email me and I will be definitely obliged to answer your queries.